Okay, so here I'm going to go through the steps of making this model we discussed in class. This is this CBAR model of the main fuselage for the Rutan Long EZ. I won't get too much into the details of why we chose the boundary conditions in the mesh, and because we talked about that in class, and likewise, I won't go into the explanation of the geometric properties and the stress recovery points and all that sort of stuff, because again we discussed that in class. I'm just going to go through the mouse clicks here. Okay, so if you're unsure as to why I'm picking some of these things, remember, just go back to the notes in class. Okay, all right, so this is the model we're going to do. It's two CBAR elements. The cross section of the fuselage is going to have the following shape. It's a little unrealistic, but it's just to make it somewhat interesting. And yeah, so let's get started, right? So when you start Hypermesh, you're going to usually get the this user profile window popping up. So make sure it's set to OptiStruct. We're always going to use that. And now we're going to go through and start the model, right? So I'll just delete this. So we're going to first make the materials, then the properties for the elements, then we're going to make the mesh, then the boundary conditions, and then set up the load cases. Okay, so let's first create the material. So we're going to make a Mat 1 card, and we'll use some quasi isotropic properties for a carbon epoxy. This is not a detailed analysis, so I'm not doing full like laminate theory on here, but suffice to say, we can consider a layup such that it's isotropic in the plane, and so we'll use Young's modulus of 7.2 million psi and a Poisson's ratio of 0.35. So for E, it's going to be 7.2 e to the 6th, and for nu, we're going to use 0.35, and that's my cat who always complains. So I don't know if you can hear her, but we'll just have to deal with her. Okay, so that's the material we'll use. Next, we're going to create the CBAR property, right? So we are going to, where's the best slide to kind of look at this? Well, okay, we're going to create the CBAR element, the property for this cross section, so we'll use these values for A, I1, and I2. So we're going to define, again, remember the orientation vector up, so that's going to be the I1 plane, right? So plane 1, that's where I1 resists the bending, so that is the bending moment about this Z element of the Z-axis of the element. So let's go here, we're going to create a property, and so we're going to change it from a P shell to a P bar, which is up here somewhere, P bar. It always gives you this warning, don't worry about it, I don't know. We'll specify the material, right? So we're going to make sure we use the one material that we defined, the quasi-isotropic carbon epoxy. And now let's put in the parameters for A, I1, I2, and J, okay? And so I forget what those are, so let me just pull these up here to the side. So for A, we used, we calculated it to be 146 square inches. For I1, the larger of the two, we calculated this to be 732,545, and for I2, the smaller, 112,601, and for J, right, we use just the simple J for the thin wall, closed section. We ignored the decking, and then we got 363.3. I probably should include the decking, but since we didn't really cover it in class, we'll just keep it at that. And those are the geometric parameters. So that is the ones that give you the stiffness, right? But remember, we also need to do the stress recovery points, right? So those go into the property as well. So we need to add the stress recovery points. So to define those, it's still in the same window, but you can see we don't really see them here. They're hidden. So as is typical with Hypermesh. So if you look at the property card for a P-bar element here, those stress recovery coordinates are on the next line, which is actually optional. So that is like a continuation line. So in Hypermesh, when we have those, you'll see this checkbox for continue one. If you click on that, it'll expose more values. These are the fields in the second line of the P-bar card. So now if you go back here, let me just pull up the slide again, you can see we have C1, C2, D1, D2, E1, E2, F1, F2, and those are all shown here. So we can put in those values, right? And remember what we used was, whoops, make sure I get it correct. So for C1, we had 0. For C2, 55 inches. For D1, minus 70 inches. This is the bottom point. D2 is 0. E1 is 0. E2 is minus 55. And again, we covered in class where these numbers are coming from, so I'm not going to go into them here. F1 is 70, and then 0. Okay? So now we have the geometric properties, A, I1, I2, and J. Those are the ones that will give you the stiffness of the element. And we've also defined the stress recovery points, C, D, E, and F, in the element coordinate system, so that OptiStruct can calculate the stresses in these elements. Alright, so there we go. So I just gotta give this a name. Let's go give it a name. Alright, so we'll do that, called fuselage bar for the bar elements. And so now we're ready to actually start making our mesh, right? So I have the coordinates here of the nodes. Remember, we're in inches, so we're defining everything in inches. The orientation vector for the elements is going to be up in global Z, so we're going to align the fuselage down the x-axis, okay? So I'm just going to go and type in the coordinates. So we go to geometry, right? We click the little geometry radio button, and we're going to make the nodes. So I click on nodes, and first one is at 0, 0, 0. So here we go. We put 0, 0, 0 in for the coordinates. I should mention, you might not see this window exactly like this when you hit node, because there are these other like options. Okay, so for example, if you had 2 lines, you could put a node at the intersection. This one, if you had 2 nodes, you could put in a number of nodes between those points. You can also seed points on a line, put them on the center of a circle. You can do all those things. Now for us, we're going to just type in the coordinates. So that is, make sure, if you don't see this, make sure you click on the little tennis ball icon here, and it'll show up, okay? So we put in 0, 0, 0. We'll create. There it is down there. All right. Next, we'll put in 4800. That's the node at sort of the primary wing chord length, so to speak. All right. And the last one is 168. there it is. So those are our 3 nodes, all right? So now we can create the element. So before I do that, I'm going to make a component collector, as we did before. So remember, these just kind of organize the elements for different parts. Like normally we're going to have many different parts that we're meshing, and so you want to give them different names so you can organize them. Like maybe for the forward wing will be on a different component level, the winglets might be on another one, so the ailerons on another level, so to speak. So we'll do that, and we'll make a component, right? So we click on component, and we'll give it a name, fuselage, okay? And that's fine, and you can see it's active. So now we're going to create the elements, and they'll be in that fuselage component layer. So to create one-dimensional elements, we're going to pick the 1D radio button here, and we are going to make bar elements. So I'm going to click on this bars button, and we are going to create a bar 2 element. There's a couple things to note here. So by default, you'll probably, the element type will be set to C-beam. As I mentioned in class, C-beams are actually preferable to C-bars, but they're a little more complicated. So we're going to click on that and change it to a C-bar, because we want to make C-bar elements. Also, the property we're going to use is the fuselage bar 1, the one we just defined. So make sure you click on that. So we have the property set and the element type set. Now we're going to define the orientation, right? And remember, for us, orientation vector, I wonder if I can get this. The orientation vector is going to be in the Z direction. That's the way we picked it. Right, remember, when I set up the problem, we wanted to use the yaw axis of the aircraft as Z, okay? So here is the way we define the orientation vector. You can pick the different axes, so we'll pick Z. You can also pick 3 points to define an orientation. You can also define a vector and select that. So, but we're going to use the Z-axis, so I'm going to pick Z-axis, and now we're good. We're going to pick the nodes. So the first node is the one at the tail, and then the one at the primary wing, and so you can see we created a C-bar element. Again, when you look at the picture, you don't know which way's up, you don't know which way is the orientation, so you have to make sure you have a piece of paper and you define those kind of all correctly before you start doing this, as we did in class. And now we'll make the second element, and so there we go. Now we have the 2 elements, all right? All right, let's make it colored by the component level, so it'll be a nice purple color. You don't have to do that, but that's fine. And fine, so we're good. We got the mesh. I'm going to get rid of these tennis balls, just because I don't like having them hang around unless I need to. They're just for construction, so we go under geometry, and these are actually temporary nodes, and we're going to clear those temporary nodes. So there's still going to be Nastran grid nodes at those locations, but we just don't need these. So I'm going to hit clear all, and they're gone away, but there are nodes there, okay? All right, so we've got our mesh, that's it. Like I said, I should probably save this, so I'm going to save it under put it in the right directory. You obviously you want to have this, but you want a different. Whenever I save, I usually give it a number, like model 1, because I might save different versions as I'm creating meshes. I try to make a mesh one way, and it doesn't quite work, so I want to save where I was before and go back to it. So I'll usually have several different models as I'm developing the mesh. But these are so simple, it's not necessary. So we saved it. Okay, so the next thing we need to do is to define the boundary conditions, the forces and the SPCs. So we'll make a load collector for the SPCs and a load collector for the forces, okay? So I'm going to do that now. So I'm going to right click in the model window here, and I'm going to create a load collector. First one will be for SPCs, and I'll do it again and create another one for the forces, okay? So you can see the last one is active, so forces is active. Let's create the SPC force. I'm sorry, the SPC constraint first. So I'm going to click on this, and if you right click on SPC, you can make it current, right? And so there we go, it's current. I'll put the forces in the wrong layer, and I'll show you how we move those in a second, okay? So to do all the boundary conditions, those are under analysis. So we're going to go to the radio buttons and click on analysis. And the SPCs are a form of constraint. So you can see here we have SPC defined. So these nodes now have all 6 degrees of freedom defined, right? Because they're beam elements, right? These are frame elements. So we're going to fix at the engine all 6 degrees of freedom. I know it's not really an appropriate boundary condition, but for where we are, we're going to keep this simple. So I'm going to set all those 6 degrees of freedom to 0. I'm going to click on the node corresponding to that point, and I'm going to create. And you can see there we created an SPC with all 6 degrees of freedom constraint. It's colored red because that corresponds to the load collector SPC. All right? Okay, so now let's make the forces. So first, I'll make the force of the forward wing, okay? The 750-pound force, lift force in the Z direction. So I'm going to deliberately make them in the wrong load collector. I'm going to make it in the SPC collector so you can see how to move them, because this does happen. And we can do the same process with organizing elements and whatnot. So it's useful to see. So I'll do that here. So like I said, I'm going to put the force in the wrong component. So let's create a force. So I'm going to click on forces. Again, all boundary conditions under the analysis button. So click on forces. I want it to be 750 pounds, and I want it to be up in the Z direction. So I'm going to pick the tip node where the primary or the forward wing is, and I'm going to hit create. And you can see there's that force, but it's red. It's in the wrong collector. So I want to move that. So the way we modify things like move elements, stretch them, rotate them, move things from one component or collector to another, it's all through this tool button. So like it has lots of tools, right, as the name would imply. So we're going to click on that, and if you put things on wrong components or collectors, we use the organize to fix that. So I'm going to click on organize, and you can see already here it wants to organize loads. So you can also do elements or surfaces or vectors or points, but we're going to do a load, and that's fine. So I'm going to click on that force, and you can see it's highlighted, and I want to move it from SPC, I want to move it to forces. So I'm going to click on destination component and change it to forces. You can also copy them, but I'm going to move it. So I'm going to click on move, and now you can see it's changed color because it's now in the forces collector. If you want to just kind of double check as well, you can toggle on and off the visibility of entities in this menu thing here. So you see when I click on the little grid looking icon, it turns off all the loads that are in that load collector. And likewise I can do the same for the SPCs. They're still there, they're just not visible. All right, so let's make this current, because I'm going to make the other forces. So I'm going to right click on forces, and I'm going to make current. So now when I create the other two forces, they'll go in there. So next we'll do the 500, we'll do this, what is it, 1,500 pound up force? Okay, so we'll do forces, we'll go back to analysis, forces, and so it's going to be 1,500 pounds in the Z direction, so it's going to be at this node here. And so we're going to create that. There it is. And lastly, we'll create the 500 pound lateral force. So that is going, the way I've drawn it here, it's in the minus Y direction. So to do that, I'm going to change this to minus 500 because it's going to go in the minus Y direction, and we're going to change this axis to Y. Click on this node, and there you go. So now we have the 500 pound force in the minus Y direction. So, right, so that looks basically like that. I'm not quite the same orientation. I guess if I do this, let's see. That kind of looks like the same orientation as the PowerPoint slide, all right? All right, very good. So we've got the boundary conditions, we've got the materials, we've got the properties, we've got the elements defined. So now we need to define the load case, all right? We're just gonna have one load case here, so we're gonna be a little simpler. So we're gonna right click in the model window again, and we're gonna create a load step. Remember, load step and load case mean the same thing. Nastran calls them load cases. OptiStruct calls it load step. So we're gonna call this, I don't know, flight load, I have no idea, right? We'll give it a name, and set the options below here for the load case. So the analysis type, right, is always going to be linear static. We pick the component level that has the SPC boundary conditions, and that's going to be our SPC load collector. There they are. And likewise for the load, we're going to pick the forces one, and there they are. We don't need to do support or MPCs or any of that sort of stuff. But we do want to change the output, because we do want to see the element forces and the SPC forces in the opti file. So, well, I'll output the displacements too, and so we're going to click on displacements and send it to an opti file. Then we will also look at the element forces. So this will give us the shears and the bending moments in each element. So we're going to do also opti there. Then we're also going to write, what's the next one we'll do? The SPC forces. So this will give us the reaction forces back here at the nodes where we have the SPCs defined. So again, we'll make that an opti file. And last is the stresses, right? So we'll do the stresses. Again, we'll put that in an opti file. Okay, so now we're going to write all those out into text files so we can look at them. So we're good to go here. We're ready to run. So again, under analysis, we're going to hit OptiStruct, and then I didn't talk much about it before, but there's like different run options here. It defaults to optimization. We're actually not running an optimization, but you can actually leave it set to optimization. I mean, technically, we're just doing an analysis, so you can toggle it to analysis, but it really doesn't matter. And so we're ready to go. I hope this will work. So let's see what happens. So we're going to run OptiStruct. It's going to save. The solver is coming up. And there it goes. The analysis completed. And I did not make any mistakes. So again, if we click on results, right, I will get, it'll load up Hyperview. All right. So let's do that. And while we're doing that, I'm going to load up the Optis files, right? What do we call those things? Okay, so here you can see is a model. Like again, we can set the deformed plots. What am I doing here? right under, pick this little icon here. We can set the deformation scale. I think it's got to be quite a bit. Let's set it at 100. Still really can't see anything, so hopefully we have some displacements. Let's make it 1,000. Huh, I'm not seeing anything. That's not a good sign. I wonder if I made a mistake. If I made a mistake, that'll be good because that will allow it. No, I do have displacement. So there they are. They're pretty small. So they're 10 to the minus 4th. So actually, let's probably use one to show you. So there you go. You can see it now if I animate it. You'll see it's coming really fast. But that's it there, right? I can show the undeformed mesh into the wireframe. Right, there it is. You can see it's deforming a little bit. It makes sense. It's bending up, right? It's because of the way we put the fixation at the engine. Like normally when we do flight loads, you would really do an inertial relief analysis, which we will talk about. But to get started, we're just making CBAR elements for now. So there you go. We can also shade it so we can see the stresses. So we can pick element stresses, and I should talk more about this. I think I'll have to probably put a pause here, but you can see there are lots of options for visualizing the stresses. So you can see we have like the longitudinal stresses. Okay, we have several of those, and you can see it's like SAC, SAD, SAE, and SAF. So the last letter, C, D, E, and F, that means the stress at those 4 recovery points, C, D, E, and F. SA means the stress, and then the A means the axial stress. So that is going to be a combination of the bending stresses, and if there were any tensile stresses due to like thrust forces or something like that down the fuselage, you would see that as well. In fact, I probably should have put a thrust force on here anyway. It would have been good, but maybe next semester I will do that. Okay, so you can see all those. You can also look at the max and min axial stresses. So like this, like let's do SA max. So this will pick the axial stress, and it'll plot the maximum in that element, whether it's at point A, B, C, I'm sorry, C, D, E, or F, okay? Here, we're just going to see the bending stresses, and then again you can see the max and the min bending stresses, all right? So if we pick axial and apply, you can see we're seeing the combination of those two. If we pick the bending one, we'll just see the bending stresses. There they are. Let's see. Right, so there you go. Okay. I'll do another video where I kind of talk more about this, and we'll do it on one where we actually have the exact solutions. Okay, so I didn't do exact solutions for this. So this is again just to show you how it clicks through. Okay. Okay. Let's close this out, and then again we will look. Let's look at the files that get written. So here's the directory where we ran everything. All right, and so again the FEM file, that's the ASCII input file. So if I open that with like say Visual Studio, text editor, you can see all the Nastran or OptiStruct cards, the CBAR, the grid points, the material, SPC definitions. These lines with the $2 signs, that just means it's a comment, okay? All right. Now let's look at the forces. So let's look at the force file. This is going to give you the element forces. So let's open that up. So there we go. So here they are, and we have one load case. So this is going to give us the axial forces, the shearing forces, the V's, these are the V's, the torque, and the bending forces, the bending moments. The first two rows are for the first element at grid points A and B, the first 2 points that are in the connectivity. And then the second 2 rows correspond to A and B of the second element. All right. So here you can see at the first node of the second element. So this is the first node of the second element. This is the 4800 point, the point that's on the quarter chord length of the main wing, or close to it. You can see that the bending moment in plane 1 is 90,000 pound-inches, okay? And basically the bending in plane 2 is 0, okay? All right. Now, in the first element, right, because we have the 500 pound force acting on it, you can see we have bending both in planes 1 and plane 2, okay? So you can see the actual bending forces in there. Like I said, you can also look at the SPC forces, you can look at the displacements, and all those things. Maybe we should just look at the displacements really quick as well. So if we go back to displacement, that's this one. Let's open that up. And here are the displacements for the 3 nodes. There's 6 columns because this corresponds to the displacements at X, Y, and Z. All right. And this is the rotation around X, around Y, and around Z in radians, okay? And so you can view all that stuff directly. You know, for one-dimensional elements, this is actually, in a lot of cases, an easier way to look at it than looking at it in hyperview. All right, so like I said, on the next example, we'll go in a little more detail about analyzing these results. But for like this video, again, like it was just to set up the model and run it. Okay, so you should be able to run this and get through it. Okay, so that is it. I'm going to stop.